Hello everyone, Team 4 and I are here today and we're going to talk to you about Mario Kart Bike Rev 2. Team 4 consists of Blake, Tyler, Ben, Ray, and Sage. Our team structure is we all divided up into parts, and then as the semester went on, we just all decided to help each other with each part. So when our schedules got tight, we helped each other and passed off roles to help out to get through the semester and get our assignments done.
In this project, our objective was to improve upon the existing Mario Kart exercise bike. To do this, we were tasked with adding variable resistance and a new mode in addition to playing Mario Kart, a ride replay mode to simulate real-life bike rides. To develop our proposal, we first stated the problem, which was to encourage gamers to exercise. Then, we identified constraints, such as providing a smooth riding experience. We also considered the ethical implications, such as the possibility of addiction. We proposed our solution, and we developed and submitted a cost estimate.
So what we're looking at right here is the conceptual design block diagram. Before we get into what the block diagram is, the conceptual design phase is the next phase after the project proposal. What we do here is we take the project proposal, we take the problem that we formulated and the solution that we proposed, and we figure out theoretically how we're going to make everything work. Not going in depth and actually designing everything, but just figuring out what we're going to do on an overhead scale and how all these little pieces that are going to be created are going to work together. A really, really good way of conveying this information is with a block diagram. Now, the block diagram takes all of our subsystems being take our entire idea, the bike and the ride replay system, and break it down into its smallest parts, and then we're going to be designing those specific small parts. And those are what each of these little blocks are on the block diagram. So right here we have detailed design completeness. The detailed design is the step that comes after the conceptual design. What this does is it takes the little subsystems that we had created in the conceptual design and we turn it into what actually exists in the physical world. How are we going to build it? Is it going to work? All of that fun stuff. That is what we are focusing on in the detailed design. In regards to completeness, we have 75% of our subsystems done. We have the resistance system control circuit, which the resistance system uses a linear actuator or linear motor. The linear motor is just this motor that moves a rod further away from its base or closer to it depending on an input, and the control circuit is informing this if it is far enough away or close enough to a flywheel. More on that later. Power distribution is how we're actually powering everything, making everything that needs electricity to run. Ride replay simulation acquisition, that is the component that is going to be hooked up to the user's bike when they're riding around, actually collecting data like elevation, speed, the actual video, and that is the information that is going to be brought back inside to create the ride replay simulation. So this is that piece of hardware with a bunch of sensors in it that is going to gather that information. The HDMI switcher, we want to be able to switch between the ride replay simulation and the Mario Kart controller all on one system. So we need an HDMI switcher so we can switch between the Nintendo Switch and the ride replay system, and that's what that is about. And then wireless sensors. The system right now has a bunch of wires that's not aesthetically pleasing and it's very not safe. So we're going to overhaul that using Bluetooth. More on that later as well. 25% of the subsystems are still in this design phase, specifically actuator mounting, which is taking that linear actuator and mounting it to a block or some sort of thing that will cause it to not fly away whenever it's moving further and closer and all of those fun things. And then steering conversion, kind of the same sort of thing as the wireless sensors, but a lot more intensive. We need to convert the steering to function in a wireless setting. So that is going to be a big thing that needs to be handled. And then 13% of our subsystems are signed off, the resistance system. The resistance system is just, in general, how does the linear actuator moving a bracket of magnets closer to an aluminum flywheel cause the resistance? So that is what is going to be discussed later. And then we also have design detail and ordering completeness. Specifically the ordering part, we have the aluminum for the flywheel and magnets ordered for the resistance system, and we still need to order all of this stuff for all of those other subsystems. Now right here we have some 3D images of the resistance system we have ordered and decided on. Excuse me. I'm not going to talk about the resistance system itself as much. I'm going to be talking about the 3D modeling aspect of it, because that was a large component of this entire endeavor. 3D modeling, if you don't know, is essentially creating an image, a digital image that is three-dimensional, so not like a picture, but like a person is three-dimensional, making something like that so people who are listening to you talk can actually look at the 3D model and be like, okay, I know what you're talking about in actual space. So we have the floor there, obviously. We have the block, which is our idea for mounting the linear actuator. The linear actuator is the thing on top of the block. We have a bracket that has magnets attached to it. And then that little circle that's connected to the even smaller circle with the wheel next to it, that is the flywheel. And that is what the bracket is going to be moving towards to produce resistance. Full disclosure, did not make that wheel, did not make that linear actuator. People who are better than me made those things. So
A few things here to where being left off at the resistance system design. So in the 3D model, you can see we have our bicycle wheel, we have our flywheel, we have the Uniski bike stand, we have our magnets, we have the bracket holding the magnets, and how it's attached to the actuator. We have our actuator, and we have our actuator box stand. So I'm going to go into detail on how it is actually going to be built here. So our flywheel, we're going to cut it out of a 1/2 inch thick aluminum sheet, and the diameter of the circle is going to be 8 inches. Then we're just going to replace the steel flywheel that is already on the Uniski bike stand with our new cut aluminum flywheel, and that'll just be one bolt. We're going to have to unbolt it, and then we'll have to bolt it right back in. So then we're going to go to our magnets and how they're being held. So we're going to cut a circle that's 4 inches wide out of steel sheet metal, and then we're going to, the reason we pick steel is so that the magnets can magnetize to the steel bracket. So if we have to add more magnets to the actual bracket later on, that we can just move them around and we won't have to permanently put them on there. So it's not dead set on how we have to have our magnets placed. But if we have to permanently put our magnets on the steel, we would JB weld them so that nothing happens, they don't come off. And our magnets are going to be 2 inches by 1/2 inch thick. And then we're going to attach our magnet bracket to the actuator by a square bracket that will be attached to the steel on the back side, and that will be welded to it, and then it will just be slided on the actuator rod that comes out and in, and it will just be pinned in there because they already have a hole drilled out on the actuator rod. And then the actuator will be attached to the box stand by a couple brackets, and they will just be drilled into the box. And then we have another subsystem that's going to attach the actuator to the bike stand, which will be talked about later on. So now I'm going to go on to the next slide and talk about the calculations behind the resistance system. So for the calculations, we use Lorenz's law to calculate the torque. And then we have a couple other equations that we used for the resistance distance between the magnets and the flywheel. So as that varies, we calculate the distance and how that affects the resistance on the little drive wheel that is turning the flywheel, and then how that is also projected onto the bicycle wheel and then projected onto the rider as the gear ratio changes. So now we're going to go on to the next slide, subsystem, the wireless sensor and Bluetooth subsystem. So to convert it to be wireless, we're going to use a little AA battery pack. We're going to use 3 AA's, which give us 4.5 volts on average, and that will give us enough current also to power everything, to make everything work. So that will cut down on the wires going along the bike stand and everything. So hopefully that makes it a lot safer, and for kids' future uses, they will not be tangled in the wires and not have to worry about your kid grabbing the wires and pulling it out and messing up the actual stuff doing the steering, sensing. And then we're going to connect a Arduino Nano 33BLE to transmit the data Bluetoothly back to the Raspberry Pi. But we're going to power all this by the 3 AA battery pack, and then we're going to power the Arduino Nano first, and then we'll use the output pins, which is 5 volts on the Arduino Nano, and power the ADS 1015, which will then also go into the potentiometer, and you'll have one input going in, one input coming out. And then the ADS 1015 converts the data to actually be read. So hopefully that is a design for how we're going to convert it to be wirelessly and still transmit our data to the Raspberry Pi to actually play the game.
So to continue on with the wireless sensor and Bluetooth subsystem, a 3 AA battery pack will be placed as shown, and this will power both the Nano 33BLE Sense microcontroller as well as the non-contact tachometer. And basically what a non-contact tachometer does is it shines a light that hits marks on a moving component like a wheel and can determine the speed from the light hitting these marks. So as you can see, the previous team that worked on the Mario Kart bike put pieces of tape around the wheel, and then the non-contact tachometer would hit these pieces of tape, or the light from the non-contact tachometer would hit these pieces of tape and then determine the speed from that. We're going to use the same non-contact tachometer, but a little bit differently. So we're going to move it down the frame of the bike a little bit so that the light shines through the wheel, hitting the spokes as it turns. And then the 33BLE Sense will be positioned on the other side of the wheel, parallel to the non-contact tachometer, so that the light shining through can hit the BLE Sense, and the BLE Sense can retrieve the speed data and send it over to the main Raspberry Pi microcontroller.
For the resistance system control circuit, we use field effect transistor H-bridge topology. This is a circuit controlling both the direction and speed of a connected motor by switching the applied voltage. This involves ECE 3300 material. An Arduino Nano microcontroller is used, which provides 10-bit precision, which is equivalent to 48.9 micrometers actuator precision, meeting our constraint for smoothness. It receives data from the ride replay system over Bluetooth. One challenge faced is ensuring control stability. To attempt to remedy this, analysis will be focused on the Arduino's ability to be used as a PID controller, and company-provided controller configuration files for the actuator used. This aspect of the subsystem will use ECE 4210 material. For the ride replay simulation acquisition subsystem, we need to collect several pieces of data from real-world bike rides in order to create a simulation: video, elevation, and speed. It is necessary to store collected data for later retrieval, and for this, an SD card rated for recording HD video is selected. Speed sensing is handled with a reed switch and spoke-mounted magnet, and elevation sensing is used in conjunction with the speed to determine the required energy input from the rider. In this schematic, you'll notice BT1 and MD1 together form the power supply. MD1 handles charging the battery and providing power to the other components. SW1 is the power switch. SW2 is a reed switch for sensing speed. And SW3 is the start and stop button for ride recording. Both SW1 and SW3 have lamps to show the status. MD2 is the altitude sensor, which has 2 cm precision. The device is capable of transferring data over Bluetooth. and it most easily relates to microcomputer systems content. Future sign-off submissions will require further numeric analysis on the sensors used and the battery life, as well as the modeling of a custom project box for 3D printing.
So right here we have the HDMI switcher that was discussed previously. Now, that graphic, not an HDMI switcher. That shows you the pins for an HDMI cable. More on that later, but what a pin is essentially a part of the hardware that you connect to an external piece of hardware. So if you have a pin on this piece of hardware over here and a pin on this piece of hardware, you can connect it using a wire. So that's what pins are, and each one has a different functionality. Like those TMDS ones represent data transfer. You have the 5-volt power one, which supplies power from that pin. That's not all super important. It's going to be a little more important in explanation in a minute. But to create this, we needed to do a little bit of research. First thing was we had some specifications we needed to meet. Because it's pretty standard and it's also what HDMI is, we needed to be able to transfer data in high definition using our microprocessor. The microprocessor or microcontroller, excuse me, in this case, is exactly that, a small controller. It tells the entire system exactly what to do. And in this case, it's a multiplexer. A multiplexer takes 2 inputs, and based on those 2 inputs, it tells something between 2 other inputs, which one of those inputs needs to become the output. In this case, it's a 2-to-1 multiplexer, meaning that we have 2 different inputs, the Mario Kart and the Ride Replay, and we want to select one to be our output, which is the TV. So it needs to be at high definition. It needs to be 2-to-1. Our components, we're looking at that microcontroller. We're looking at the ports for the 3 HDMI cables, and we're looking at a bunch of resistors. All resistors are pieces of electrical hardware that prevents current being just effectively the flow of electricity in a wire, from destroying different components when it's too much electricity. And then the connections are those pins we talked about. So the microcontroller has pins on it that correspond to the pins on an HDMI cable. And to make sure everything runs smoothly, we need to connect the correct pins to the correct pins. So that is what the entire purpose of that is. The schematic comes up next, and then topics I learned for this came from ECE 4140. That's embedded system design. This is a very simple one, but it's an embedded system using a multiplexer microcontroller and these and the HDMI cables and ports. And then right here we have the schematic. The main thing that's important about the schematic is you see the 3 blocks on the left side, the 1 block on the right side. I don't know if that was the correct order with my camera. Don't worry about it. And then all of those red little connections. The red connections are the pins that we talked about. And then the 3 blocks on the left are the HDMI ports. And then the box on the right is the multiplexer. And if you look closely, you can see that every single one of those pins connects to a corresponding pin on the microcontroller. And that is so everything can run smoothly.
The subsystem that I individually designed was the power distribution subsystem. Now this subsystem's objective is to receive 120 volt AC power from an ordinary outlet or wall receptacle and then distribute that power throughout our simulator or subsystem that require both AC and DC. So we have 3 converters in this subsystem that convert 120 volts to either 15 volts DC for like the Nintendo Switch, or 5 volts for items like the fans or the main controller that's located within the power distribution box, or we have a 12 volt DC linear actuator motor that we power up as well. So the main learning objective here was to be able to design a system that is both reliable and safe, and that is a balance. You want the system to be safe and have protections like circuit breakers or fuses. However, you don't want to have it overprotected where it is continuously going offline. So for that, I reached into the National Electrical Code, and they have a recommendation of using or sizing your wire and circuit breakers and any other protection devices such as fuses by 125% rule or an 80% rule. It just depends how we look at it, which direction. But the main thing is you would take the total current of a device that it could possibly, its full rated current that you can see, and then you raise it by 25%, and then you set your protection or your wire size based on that number. So that allows you some wiggle room to be able to safely protect your device and your equipment, but also not have it continuously going offline. Another opportunity for learning was AutoCAD Electrical. This project allowed me to be able to use AutoCAD Electrical to design a power distribution box, specifically for our needs. So the power distribution box that we have currently, as you can see, it's quite messy, and there's wires all over the place, and the converters are just simple plug-in converters, and we are going to propose that we clean everything up, make it organized, which will increase the safety. Of course, it's very hard to be safe whenever wires are not well organized, and so we're going to increase ability of safety, and also overall it'll be better for troubleshooting if there is any troubleshooting required in the future. But as you can see, there's quite a difference between what is proposed and the current. So this looks like to be a huge improvement.
So here are subsystems that are still in design phase. The first one is the actuator mounting. This subsystem we are tasked to attach the actuator to the bike stand. And our idea for this right now is to use a 1.5 inch 2-hole tube strap, which would go around the Unity bike stand tube, as you can see in the 3D model, and it would be attached to the box that is holding the actuator, and you just use 2 screws, one on top, one on the bottom, to fasten it to the bike stand. And since the Unity bike stand sticks out roughly around 8 inches past the flywheel, that would give us multiple room. If we had to use more than just one or two, we could still use multiple straps to secure it to the bike stand. So we believe that will attach the actuator to the bike stand securely so that it doesn't get slung around the room or kicked if someone's getting off the bike or something like that. So onto our next subsystem, the steering conversion. So we are converting the 3D printed gears and L bracket to be metal. So for the gears, we're planning on using hopefully the leftover aluminum we have. We will cut the gears out of it, which is a 1/2 inch thick. And the reason we picked aluminum is because it is lighter than steel and iron. And then hopefully we can buy an L bracket off from Lowe's, which could be steel most likely, and this would have enough support so we could get rid of the screwdriver there that's in the picture, and that would we'd have one L bracket, which would clean it up. So because with it being metal, you would have enough force in the metal that you could bend it to where the gears would be tightly pressed against each other. And then for the gear that is going to be around the steering column, there will be a 1 inch hole cut in the center of it, and it will also be cut in half to be able to go around the steering column. So as we go to the next slide, you can see how the last team, they just drilled a screw at a 45-degree angle into both pieces of the gear. So our plan is to still do the same thing, but when we convert it to metal, we will have to drill a hole almost through both pieces before we cut it, so it's not difficult. Then we will cut it, and we will, on the second half that the screw will be going into, we will tap that so that we can use a bolt or a screw and tighten it so the bolt will thread into where it has been tapped, the half of the gear where it's been tapped, so which would tie it in. We'll pull it completely in tight around the steering column So that would keep our gear wheel from moving and sliding back and forth and be secured tight to that steering column. And we believe that will fix the problem from where the last team had the L bracket break and then the steering wasn't as efficient as it should have been.
As previously mentioned, our problem definition is to encourage gamers to exercise. We formulated our problem as adding a better source of resistance and more interesting riding options to the current solution. In doing this, we defined certain specifications which our design was required to meet. In our conceptual design, we identified useful sources, considered the standards relevant to the project, and determined our approach to tackling constraints. In detailed design and analysis, it took several iterations of each idea and much back and forth with each other as well as professors in order to arrive at the solutions we have now.
So looking at professional considerations, a big consideration was Nintendo copyright laws, which basically are laws that protect Nintendo's intellectual property, like Mario Kart. Uh, a big part of this is that it limits our access to game code, which is important when we try to implement our resistance system in Mario Kart. Uh, so in order to bypass this, we decided to do rumble state acquisition, which is basically just looking at different vibration states in game and being able to assign resistance systems when certain events happen, like say driving off the track or being hit by a item. Uh, each of these will provide different vibration states or rumble states, and then we will be able to apply the resistance needed for each of these. And then also the aesthetics of design. The current design has a lot of exposed wiring and sensors, which isn't something you really see like products on the market. So we're going to improve this and try to make it more wireless, so that it lines up more to something you'd see in real life or something you'd see on the market. Uh, Ethical considerations. A big one is the video game addiction trend. More people are becoming addicted to video games as time goes on, and by using this bike, they would be spending more time indoors gaming, which could potentially contribute to video game addiction. So we are going to try to solve that a little bit by having a message pop up every hour or so that informs the user of their playing time, just so that it gives them some perspective on how long they've been playing, so they don't maybe play it all day if they really enjoy using the bike. Looking at standards, we have IEEE 802.15.1. This is basically just the protocol for Bluetooth and Bluetooth Low Energy Communication. Specifically, we're going to be using Bluetooth Low Energy, and this standard just basically goes over how Bluetooth communicates and like what sort of frequencies it operates on, things like that. And then also OSHA 1910.137. This is standard for electrical protective equipment. We will be dealing with electricity, and this standard is really important because it gives tests for determining the effectiveness of electrical protective equipment. And so when we will be dealing with electricity, we are going to determine these tests on the protective equipment we use, so that we can know for sure if it passes the standard. Here are relevant classes. These are classes that have been relevant for components we've worked on, as well as some classes that we anticipate will be relevant looking down the line. So you see there's a lot of ECE classes in here, as well as CSC classes, which mainly deal with the software and coding side of things, and then physics classes, which mainly deal with the hardware, specifically the resistance system so far. STEM topics, these are more specific topics or classes that apply to each subsystem. The main one we've been working on, the resistance subsystem, dealt heavily with eddy currents, which are those classes listed, as well as MATLAB coding and graphing. The resistance system controller subsystem used controls design as well as electronics. The wireless sensor and Bluetooth subsystem that I personally worked on, as well as Blake, deals with data transmission, C++ coding, as well as general electronics. HDMI switcher subsystem deals with the schematic design and microcontrollers class. Power distribution subsystem works with power electronics, as well as circuits 1 and 2. And then finally, ride replay simulation data acquisition involves general coding as well as sampling from those classes. So looking at engineering decision making, I think this process was most evident in designing our resistance system, namely our flywheel in the resistance system. Our original idea overwent numerous changes before we finally arrived to a design that would work. So we started off with thinking of putting aluminum plates on each side of the bike tire, basically creating a flywheel, and then applying the torque to those aluminum plates. But after consulting with Dr. Van Nest, it was basically determined that this wouldn't work, as this bike tire wouldn't generate enough speed, and this design just wouldn't produce enough torque to really work at all. So from here, we came up with the decision to maybe replace the bike tire completely with a solid slab of aluminum, basically a circular aluminum tire with a hole in the middle. And we kind of thought that, this would improve the original plate design, and maybe the additional aluminum from replacing the wheel would be able to generate more torque. But after talking with Mr. Roberts, he kind of explained to us that it's a lot more difficult to make a wheel than just cut a circular aluminum shape with a hole in the middle and then just put it on there. It's quite a bit more complicated. So he recommended the wire wrapping around the tire, which is basically just wrapping aluminum wire around and then applying the torque to that wire. And we were really going to go with that, but then we realized that we could actually just apply the torque to a little flywheel in the back that's basically attached to the main bike tire. And because of how the gearing and size ratio of the bike tire to the little flywheel works, we can apply lots of torque to the big bike tire when we apply the torque directly to the flywheel. As the flywheel, when the rider is pedaling, spins at a much faster rate than the actual bike tire, so this will be able to generate a lot more torque. As eddy currents work, the faster the wheel's turning and the closer the magnets are, the more torque's produced. So if you've got a little flywheel moving really, really fast, you can generate lots of torque, and then that torque is converted to the main bike tire through the gearing ratio. And so you can really see how it went from one thing to the next, to the next, to the next, and then finally get to the conclusion after quite a bit of trial and error. And so on the right, we listed the specific sources that we consulted with: Dr. Van Ness, Mr. Roberts, Dr. Schreiner, and machine shop personnel. They all assisted in this decision-making process, and we would like to thank them.
We had 4 significant milestones that we reached during this project, the first phase of this project. 4 of them being first the project proposal, which we were able to complete on time. The conceptual design also met on time. The design checkpoint was a team subsystem, such as our resistance system. We met that on time with above 60% complete. And then our last checkpoint, our last milestone, was the checkpoint 2, which included both the final of the resistance, the team subsystem, then also our initial individual designs. And we had some challenges on this portion of it, and we were actually 7 days past due for this checkpoint, mainly because of the team design challenges that we faced. Going further on that, some of the setbacks we had were the flywheel of our resistance system. We actually had 4 different designs. One being modifying the current rear tire that's on there, and then another is actually removing that tire and building a new tire. That seemed to be the most challenging because that was very mechanically involved. And then we ended up finding an option of using the existing stands flywheel where the back tire sits on and rotates. We used that system, but we just enlarged the flywheel that's on there to make it work for our purposes in generating eddy currents. Another challenge that we had for the resistance system is the 3D modeling. All of us have very limited 3D modeling experience, and Ben really stepped up to the plate and was able to gain knowledge on the 3D modeling, so he came through with that. But there was definitely a delay due to that, I guess, learning curve. I also think team collaboration and schedule. Out of 5 of us, I think we had maybe possibly 3 hours out of the week where not all of us was in classes at the same time. So that made it really difficult. So a lot of our planning was outside of the meetings that we have via Discord or texting. So that was definitely challenging. Was getting the time to link up with everybody, because it seemed like the best time to work on something is with us together rather than sending ideas back and forth via Discord. And another challenge that we had that affected the timeline was understanding the stakeholders' position and their perspective. Whenever you're building something, you're intimately involved in it. So sometimes things are just in your mind, you know how it works. However, on paper, it's hard to be clear and concise so that the stakeholder understands what you're trying to do. So that was definitely a challenge. Lessons that we learned, one of the things was identifying the problem early, so that way we can minimize delays, such as the 7 days past due. The flywheel should have been our main focus, and being able to figure out how to mount it properly, and discounting out things early. Like we should have been able to discount the mounting of a brand new tire fairly early because of the mechanical obstacles there. So, identifying the problem early is definitely something we need to work on. Also, honing in on our skills for 3D modeling is something that we all of us need to work on. And then not being afraid to seek out outside advice, such as our supervisor or the teaching assistant, so that way we can get an outside perspective, so that way whenever we present these to our stakeholders, it's very clear and concise. So for the future, we plan to communicate more effectively and understanding the problems as well. So we communicate there is a problem, but understanding what the problem is and how to fix it we plan to improve that. Also, beginning things early as possible. That's another thing that we can improve on. And then assigning team members into groups for like subtasks, I think that would be helpful. We all think that'd be helpful to minimize confusion for who's doing what for things whenever we're working with the team. So that's definitely things that we want to work with, and then also reaching out to our supervisor and TA for outside perspectives. So our approach to time management, we originally began with meeting once a week for an hour and a half, and then we would work separately after that. We would have Discord and text, but that quickly evolved to meeting multiple times a week with the limited time that we have, and then we ended up just being constant communication was involved, day, night, through Discord and Zoom. So it really became evolved into a very extensive time management approach of keeping everybody aware of things that are due and what we need to accomplish. Some problems that we faced, I did spoke earlier about the flywheel for the resistance system. That was the huge problem. We ended up resolving that using the stand. That was the flywheel on the stand, and modifying that. Another problem that we faced was the drive wheel, or the actual pedal wheel. We wanted to make sure that whenever we were putting resistance on the system, we didn't put too much torque in there that we could injure somebody. So that was, we were able to resolve that by being able to move the magnets away to decrease the resistance. So we had a strategy for moving those out there. So eliminate that possibility. And then another problem we ran into was the stability of the motor itself for moving the magnets in the resistance system. That was kind of free floating, and we realized that through help with our supervisor that we needed to mount it on something that is very stable, such as the stand or the bike itself. So we are working on the bracket for that. And then I briefly spoke with this, but the 3D modeling, that's definitely a problem, and we're all going to work to become better at 3D modeling because we'll need it throughout the project or any project. And then skills that we acquired, or there's many skills that we all acquired, everybody individually differently, but the main thing was time management. Seeing that we all had different schedules, time management was key to this project. Project management, understanding the scope, that was definitely a skill that we scope and constraints of the project. Those were definitely aspects that we really were focused on and improved upon. Collaborating with our peers was definitely another one that we improved on. We definitely all speak and communicate very regularly. And then also our technical writing definitely increased and improved throughout the process of revisions and working and getting things continuously improving on our writing. AutoCAD, we all improved throughout our individual designs and as well the team design on AutoCAD. And then we also learned some more about eddy currents, where our current courses, there's eddy currents. We learned about eddy currents, but we really had to focus in on the eddy current generation. Our resistance system was ultimately signed off. We did end up have to pull the linear motor design into its own subsystem, as we were saying, the bracket, so that way we could stabilize it, and then also be able to work on the circuitry for that. We have an H bridge already, which is a motor controller already in the works. So that's going on pretty smoothly. We need to get our individual subsystems all signed off. So that's the next steps for us. And then there will be definitely a couple more subsystems as we progress that we need to either touch up or if something comes up. throughout the process. We need to, design for that. And also we have some materials that we have to actually order to complete the system. So that's our plan for the future. I just wanted to thank you guys for coming to our presentation, and we really enjoyed this first half of the project. And our next slide is going to be just our references that we use throughout this PowerPoint. But again, I wanted to thank you guys, and hope you have a great day.